Good evening, everybody. My name is Paul Delaney, Second Vice President of the Toronto Centre of the RASC, and I'd like to welcome you to our Speakers Evening for Wednesday, February 12. Before we get underway, do we have some newcomers to the evening? Everybody is present from past. Okay, we can go with that, not a problem. But just in case you have forgotten, there are, of course, two types of meetings. There's this one, once a month, the Speakers Evening, and I'll be introducing our speaker in just a moment. And then 2 weeks from now, of course, is the Recreational Astronomy Night, where you all have your chance to tell us what you have or have not observed, have or have not built of late. At any rate, that's 2 weeks from now. For the time being, it's my great pleasure to introduce one of the PhD students from York University. Yes, York University is a regular staple at these evenings. It's okay, you've only got another few months of it. But Richard Bloch is actually familiar to everybody in this room because, of course, he was the RASC Gold Medal winner 2016, right? Yes, so we've finally dragged him back to give us an update on what he is up to. Just to refresh your memory, he joined York all the way back in 2010, although the first couple of years he couldn't quite figure out what he should be doing, and then he moved in, he saw the light. 2012, joined the observatory team there at the Allen I. Carswell Observatory, stayed with us through till 2016, where he graduated, charged over to Western, picked up a master's degree there, again, saw the light, came back to York last year, and he is working on basically general relativity cosmology, with Matt Johnson at this point in time, so well into his PhD. So tonight he is going to be giving a presentation, something that we all want more of, something about time. Richard.
All right, thanks everyone for coming, and Paul and RSC for having me. This is really exciting. One of the things this is really exciting about for me is I get to talk about time, which is a really interesting topic, but it's sort of hard to study. It's not something you can like pick up in the lab and put in a machine and stuff. But it's so fundamental to how we live. It's sort of, it's going to be on time, and I hope to shatter some expectations about what you think time will be. So the whole point of the talk is to answer this question: what is time? Or at least provide an answer that is somewhat convincing to you guys. So to do that, I'm going to go through sort of 4 areas of approach. First, we're just going to look at how have people thought about time through history. I'm not the first person to talk about time, and even though we've all probably thought about time, we're not the first people to think about it. So what can we learn from what we've already learned? And then doing that, we're actually going to see that the question, what is time, can be a little ambiguous. It can actually have a couple different meanings depending on what we're talking about, as you'll see. And so we'll see that we'll have to sort of deal with time as we know it and time as physics knows it. So we'll talk a little bit about what is time in physics, why is it different from our time, what's similar. And at the end of the talk, I'm going to have to explain how if physics has a different time, if it's not so easy to just ask what is time in general, I got to have some way to explain why, if time is so different in physics, we get us, and we have such a strong experience of time. So we'll just jump right in. Time throughout history. So this is sort of a good place to start asking about what is time, because we actually have had a couple relationships with time through human civilization. One is our daily experiences, like our lived life. We feel the flow of time, right? I've started talking, you get a sense that the talk is underway. You know, if time is a line and we're just slightly into the talk and most of it's left to go, you know what I've said, you don't know what I'm gonna say. The behavior of time is really familiar to us in these ways. And so we'll talk a little bit about that, but we'll also see what science has had to say. How have people studied time and thought about time throughout history, and what do these two perspectives have to offer us? So the first thing is experiencing time. So we can probably assume, because anthropologically we have been this type of human for tens of thousands of years, that the actual feeling of living probably hasn't changed throughout human life. But the way that we think about time has changed. So in the pre-industrial era, we didn't have time zones and standardized time and any of this stuff. Each town kept its own time, and it did that with like a sundial. And the sundial is really useful because, it tells you when is noon, when is sunrise, when is sunset. Well, you don't need a sundial to tell you when sunrise is. And it was local. If a town was 15 minutes or 10 minutes offset from another town, it didn't matter, right? You would go to town on your horse. It's not like you could communicate any faster. And if you needed the time, you would get the local time. And strangely to us, because we have a 24-hour day and each hour is the same and time is consistently ticking by, so we think, but they didn't structure time that way. For them, it was an agrarian society. It was more important to have a fixed number of hours. So between sunrise and sunset, because that was how you were going to structure your day. But we know, especially in Canada, that in the summer, if you do that, your hours are going to be longer than your hours in the winter. So it's weird to us, and it's not very useful to us to have hours that shift in time, but it didn't matter to them because that's just not how they needed to live their life. And for most of human history, this is actually how it was. They could keep time at night, and they could do lunar calendars to keep track of the seasons. And it wasn't really until the Industrial Revolution that we developed the sense of time that we feel here and we think is just sort of natural. And that sort of came from the invention of trains and the telegraph. So with the telegraph, we can communicate faster than we can travel. And with trains, it's really important that we have standardized time. Because if you have every town has its own time, and you have a train schedule, and you leave, and then you come back, when you're one station away from where you've left, your schedule is already wrong. Right? Because the schedule you would get from that town would tell you something different. And the farther you go, the more stops you go, the worse this problem gets. So it was immediately clear that we needed some sort of standardization if we were going to start behaving on much larger scales. And that's when, later, still in the industrial times, we find the invention of time zones and setting standard time. And this is sort of blown up with the information age just recently with the internet. We can email, we can Skype across the world. It seems instantaneous. Like we all share this present time. And if anything, it's just been technology getting in the way of us being able to access it. And the better technology we do, the better and better we'll get there. UTC, to astronomers especially, it's like, that's the time, right? There is a time on Earth, and that's now. And an atomic clock keeps that time to a millionth of a millionth of a millionth of a second. And you can have your computer synchronized to it, within milliseconds of accuracy. It's all very good. It's all very nice. But it's really only recently that we've been thinking about time and had this obsession with keeping it consistent, having this thing that's going, and can we measure it? And this isn't just a day-to-day life thing either. I mean, so I said we would think about scientific thought. And so if we want to talk about time in science, we go back to Aristotle. He was the first one that we know of to have thought about time in a scientific way and written it down. He may not have been the first one, but that's what survived. And Aristotle, in the pre-industrial time where he wasn't thinking about this consistent, driving force of our life, he said, time is nothing special. Time is just how we measure change. If something changes, we say time has passed. If something has not changed, we say no time has passed. So that's sort of a weird way of thinking of it. It's partially maybe intuitive because it's true, things change in time and we're used to this. But it's kind of weird in the sense that, if I had superpowers and I could freeze this room for like 5 minutes, and then after 5 minutes is over, we all just resume moving again. And for those 5 minutes, nothing was happening. No biological processes, nothing in your body, whatever. We would sort of understand, okay, well, we might not notice that 5 minutes has gone by because we couldn't, if that was the rule of the game. But we sort of picture, well, there's this, somehow there's this 5 minutes that has gone by, this fundamental 5 minutes that's there. We just can't access it or see it. And to Aristotle, that would be nonsense. He would say, I don't know what you're talking about. This, what, in no realm does this 5 minutes exist. If you couldn't tell that something's changed, there's no time. Period. And it's a weird way to think about it. And it gets even weirder because Aristotle really didn't think time was special. He said time is a way to measure change. It's not the only form of change there is, which also makes sense. We know, for example, temperature changes from place to place. Whether or not you want to run a clock in the background, the temperature is different at every point in this room, slightly different, right? All you need to say that there's a change is you compare two different things. And if they're the same, you say nothing has changed. And if they're different, then you say something's changed. The temperature is the same here and here. I say there's no change between here and here. If the temperature is different, I say there is. So for Aristotle, time wasn't even something fundamental or special. It was just another type of thing that could measure change. The more stuff that changed, the more time has passed. And that's all there is to it. And that didn't have any conflict with the way that people lived their lives at the time. They were like, okay, seems fine. And that actually reigned as scientific thought until Isaac Newton. So like 1,500 years of time not being this fundamental thing that we experience. But Isaac Newton changed that. You'll probably like what he has to say, because he says, well, no, time is this fundamental thing in the universe. It ticks away everywhere for everyone, and there's a flow to it. It goes from the past to the future. It goes through the present, and it's something that's so fundamental to the universe we can't even access it. Like I said, you can't take time and put it in a box. You can't go into a lab and measure time. It's sort of, but the laws of physics we know follow time, right? You can ask how do things evolve in time in physics. So we live with the consequences of physics, right? Laws of physics tell you how do electrons move and will you bend if you go around this corner and all these other things. And the laws of physics, that just as we listen to the laws of physics, Newton says, listen to time. And so the laws of physics is the middleman for us. And we can't actually access time. So time is this super fundamental thing by which even the laws of physics are bound. Now in this picture, where time is ticking away everywhere in past and future, for Newton, time, the now, the present, is the same for all of us. Now here is now everywhere. Time is this fundamental thing. There's a universal time happening, ticking away. So this is the Betelgeuse has already exploded, but we have yet to see it model. So there was in the news recently, you know, Betelgeuse was dimming and there was a lot of excitement. Could it be going supernova? Because we know it should be going supernova soon. But Betelgeuse is 640 light years away. So there was also talk that, well, maybe it did go supernova sometime in the last 600 years, but we just haven't seen it yet because the light has yet to catch up to us. And that's sort of the Newton picture, that there was a moment, right, like here and now, that is also happening in Betelgeuse. We can't see it because light takes some time to travel, but that's fine. That says that's nothing. There's still a universal perpetual now. Just because we receive delayed information doesn't take away from this fundamental now. And that seems pretty reasonable. That seems to be okay with the way we experience time, and it certainly was great with the way that we interacted with the world, with standardizing time and using this formulation to make predictions in physics. And for all we know, we'd still be there if it weren't for this man, Albert Einstein, who has a really bad habit of just going into well-described physics and ruining everything, but being so right you can't argue with it. So there he is, being all smart. Einstein said something really strange and profound. He said, Aristotle and Newton are both right and they're both wrong. There is something called time. Aristotle was a little too flippant when he disregarded it entirely. There's some physical thing we can call time. But Newton was wrong to say that it was a fundamental physical thing. Time is not fundamental. Instead, what is fundamental is gravity. Einstein said gravity is the fundamental physical quantity. And time and space, or time in particular for this talk, just probes the gravitational field. So again, you might have heard that, or if you haven't, you'll hear now, that time can run differently on the floor than on a mountaintop. The closer you are to the ground, the slower time will move for you compared to somebody who lives like way up high. And this is not just a calculation thing. We've done this on the tabletop in a lab with centimeters of difference and been able to measure with atomic clocks that time passes differently. And so time is just probing the gravitational field. What happens is you say, well, I'm going to take two clocks and I'm going to synchronize them. They're both 0. And one of these clocks I'm going to take around here and I'm going to come back. And if they're not synchronized anymore, that's not because something is weird with a fundamental thing of time. That's just telling me something about the gravity in this area. And so you actually need both space and time, right? Because if I said you take a clock and they're synchronized and you move it around here, so there's a notion of space, right? Space and time is passing. That's why if you ever hear talk with relativity, you always hear space-time as one word, because you can't extract space and time from each other. They're both probing gravity. Gravity is the fundamental physical thing, and you need space and time to do that. And gravity, if you just think about gravity for a second, gravity, we sort of understand how this works. Gravity changes from place to place, right? If you're far from the Earth, you're going to fall slowly. If you're close to the Earth, you're going to fall faster. You know, when you're around the sun, and it can determine the orbits of the planets, their speed, all these things are determined by changes in place to place. So if gravity is changing from place to place, then the things that we use to probe gravity also have to change from place to place. It's just how it works, right? If you say, well, the temperature in this room changes from place to place, right? And you say, well, how much energy is in that temperature? Well, if I dial the temperature up and down, you're going to get a different amount of energy out, right? So if I dial the gravitational field up and down, you're going to get different times out. It's a weird way to think, and it sort of asks you to make a leap of faith in something that, you know, doesn't have an everyday experience to associate yourself with. But that's the logic. That time is really just a probe of gravity, and because gravity can change from place to place, so can time. And so now we run into a problem, because if time can change from place to place, then if it's now for me here, it's not necessarily now for somebody right there. Because if gravity is different and then time is different, then I can't possibly say it's the same time for both of us, because it's not the same gravity for both of us. So we're running into a problem already when we ask what is time. And this is what I meant when I said that we're going to have to diverge and go down two different paths to talk about time. Because in human time, one of the most fundamental things that we experience is we share the now, right? We're all in this room and we seem to be sharing a now. We know that, okay, well, you know, light travels at a certain speed and this distance, and so there's a, you know, minuscule difference, but it doesn't matter, right? That's still the fundamental human thing. There's a now, and in physics there is no now. So we'll have to not just ask what is time, but we'll have to ask what is time in these two contexts, and then see how they fit together. So the first one we'll do is human time, because human time is sort of the one we're most familiar with. And we like to think of ourselves as like flies on the wall of the universe. So we think we're in the universe and we're part of the universe, but you know, maybe we're limited by our senses. We recognize, for example, we can't see X-rays and we can't hear dog whistles. And we can even imagine, if you want to be creative, you know, that there are senses that we don't possess as humans that might be possessible. And so there are things we're missing. And we're okay with that. We say, okay, well, we'll work within our senses and we'll have math and experiments to try and help us access what's outside of our senses. And we sort of think of ourselves as, you know, we can't see the whole universe, but we can see a part of it. And the part we can see, at least we can see. But I'm going to sort of step out on a limb from that and say, that's not quite the best way to think about it, but rather that we don't see a windowed version of the universe, we see an approximation of the universe. We learn an approximation of the universe. And what do I mean by that? So a good example is with time, because this is the point of the talk. So we, as people, we're outlived by our possessions. Okay, there's family heirlooms, people bequeath things in wills. You know, stuff can last longer than us. And if you look at the pyramids, you know, then you know buildings can outlast their civilizations, right? And these can be long, long periods of time. Like the ancient Romans are as far ago to us as the pyramids were to the ancient Romans. And yet we don't talk about things on scales like out to the dinosaurs or planetary time or the history of the universe. We don't compare ourselves to this because it's ridiculous. We're too short-lived. And as a result, we have a skewed perspective on the universe. We think the universe is made up of things, and we chart the history of things. So this clicker, this PowerPoint clicker is a thing, and I'm holding it, right? And it was down by my side a moment ago, and now it's up, and I'm waving it around, and then later it'll be down by my side again. And we think, okay, that's how the universe works. It works. It's full of things, and then you have physics, which tells you how the things behave. And then we can maybe just sort of be flies on the wall and see the things happen. So that's sort of the perspective we get on the universe from who and what we are, and I want to tell you why that's wrong. And there's a really, really, I think, straightforward way to sort of show why it's got to be an approximation and not just part of the universe. So we have this basketball, okay? And this is a lesson you would have learned when you were a child. So you go and you have a basketball or something, and you put it in a room, and you walk away, okay? And then you come back in a bit, and it's still there, and you play with it again or whatever. So good, you learned that it'll stay there if you leave it alone. But maybe you come back sometimes, not often, but sometimes, and it's gone. And quickly enough, you find out that your parents or your siblings or somebody moved it or put it away or played with it. And you go, okay, well, it stays where it is unless something interacts with it. People can move it and whatever. Otherwise, its natural tendency is to stay where it is. So we're learning, when we're doing this, we're not learning how the universe works. We're not learning fundamental things about motion in the universe. We're learning how basketballs work and how we interact with basketballs. But we don't realize this because not only does it seem really obvious, but then we go to school and we take a physics class and we learn Newton's first law, that unless a force is exerted on you, an external force, your state of motion is not going to change. And we go so far as to call it a law of physics. And we're like, okay, well, first, that is totally sensible given what we've seen and experienced, and I don't doubt that this has got to be true, and it makes a lot of sense, and we can do a lot of good physics with this. But this is not true. The universe is unintuitive. This is not how the universe works. This is how our approximation works. Because if I were to take a particle instead of a basketball, and I take the particle and I put the particle in the room, we know from quantum mechanics that if I come back and I look again for that particle and I don't find it, I can ask my family and they will answer truthfully, no, I didn't touch your particle, but it will still not be there anymore. And even worse, we also know from quantum mechanics that maybe it was there until you went back to look for it, and in the act of looking for it, you made it disappear and go to somewhere else. This is ridiculous. But if we grew up in a world of particles and not basketballs, it would be like, well, of course. What do you mean the basketball would be in the same place every time? What's so special about that place that things always appear to be there? Right? And now you want to say, well, that's ridiculous. So we get, it's the approximation we learn, right? Particles might suddenly be found elsewhere. They don't have a specific place. They have wherever they are when you look for them. I mean, there's probabilities for it, but they have whatever they are when you look for them. So we don't learn about the universe. We learn our approximation. We learn how to live in a world of objects, not particles, because we evolved to live in this world, to survive in this world. And one of the things that it turns out is a strong feature of the world of objects is time, as we experience it. Time. Time is not some fundamental background thing that is party to both objects and particles. Time is a part of the world of objects. It is not a part of the world of particles. And we are just familiar with the world of objects. And that's it. And we know that's it because if we say, well, we really feel strongly that there's some kind of time, let's go out into physics and find that time. We've already seen from just a cursory look from Einstein that we can't find it. We can find something sort of like it, but we can't find it. It's not there. So let's talk about what we find in a little more detail. So we're familiar with human time, but really what's the physics telling us? So we already know a little bit from earlier that the physics tells us that there is no universal one time, right? There's times for every place. So every place has its own clock. Okay, and when I say that, again, we tend to think of time zones, and we're like, okay, well here, these places have their own clock. 10 a.m. in Vancouver is 1 p.m. in Toronto. But that's different. That's not what I mean, right? Because 10 a.m. in Vancouver, 1 p.m. in Toronto is telling you that there's still a shared now, but we're putting different labels on it. And that's not what I mean. Remember this picture from Newton. Newton would say, we have different labels, right? You can set the clock to whatever. But behind this wall is one gear that turns all of them, the same speed. And all physics will do for you is tell you how to translate between whatever a particular clock's reading is and the master reading on the master cog. Okay, and that's what we like to think. We like to think there is a time that's turning. There's a gear behind the wall. And what Einstein told us is there is no gear behind the wall. Every one of these clocks is its own clock, and it's valid. Each clock is as right as any other clock. It's like asking, when is noon? You can't ask when is noon. It's a meaningless question. You have to ask when is noon in a place. When is noon in Beijing? 3 hours from now. When is noon in Toronto? Tomorrow. We missed it, right? You can't just say when is noon on Earth? When is noon on Mars? And so what makes this worse, actually, is Einstein also told us that these clocks, not only do they not have to match, they don't even have to run with the same rate. Okay? So we'll still call them London and Hong Kong. You can see that they've got two different times on them. And in time zones, that's really nice, right? 10 a.m. in Vancouver is 1 p.m. in Toronto. That was true today. That will be true tomorrow. That will be true in 5 years. As long as they don't change time zones, right? And we still keep 24 hours in the day, that will be true. But if clocks can run at the same rate, that's not true. Maybe we synchronize 10 a.m. and 1 p.m. today. Now we don't know if tomorrow they'll even be synchronized anymore. So we're really getting into trouble with time in physics. And we also know that the way to make clocks move at different speeds, you have lots of options and they're really easy to trigger. For example, motion, right? If you get somebody goes in a plane, you got their twin on Earth, They go flying around and they come back. They won't look it, but they are younger. Because things that move through less time. Same thing on Earth. When you're closer to the ground, you have less time. Your head is older than your feet. You don't feel it, but it's true. So all clocks are valid. All clocks. Every place has its own clock, and every clock is equally valid. And in order to understand this, we're going to have to talk about events. In order to really hit home, because I find that I can say this thing a lot, like all clocks are valid, and we go like, yeah, okay, I believe all clocks are valid. But then really quickly, when we start talking about physics, it comes back down to, okay, but there's something really going on. What's the real story? And what I want to do is I want to explain to you how there is no real story, how it can be that every clock is right. So Einstein said something really crazy, which is the world is not made of things. Okay, it's not made of this thing that has its own history and goes through space and I'm a thing and whatever. The world's made of events. What's an event? An event is anything that happens in a place and a time. Okay, so like a high five. If you high five somebody, that's an event. It happened here and it happened now, right? And I can't ask, where will that high five be tomorrow? Like nowhere. You can high five again. You could recreate the high five, but that high five is gone. It's an event. It's a one-off. It's not like a party event, right? A 3-hour-long thing. In a weird way, a 3-hour-long party is a series of events, right? It's like a movie is made up of many, many small frames, and they move too fast for you to really tell that there's granularity there. In the same way, all these things, when I hold this up, you see this thing. You're not actually seeing this thing. You're registering a series of events, many trillions of photons hitting your eye. And if you slow down time enough, if you could, with magic or whatever, you would one by one these events, and you would record, okay, new photon came in this place this time. Next, photon came in this place this time. So that's all you have to say, because you're not interacting with this, right? You're interacting with the light that came from it. And that has some really bizarre consequences, because if every clock has its own, so every place has its own clock, then if you're recording, every time you receive a light from this thing, every time it blinks, I'll blink it. Every time you see that light flash, okay? And you record. Obviously, you're going to record different positions and different times for when you recognize this event has happened, right? You're all sitting in different places, so by definition, you'll record a different position. And then some of you are sitting farther back, some of you sitting closer up, so you'll also record different times. Those in the front row will see it before those in the back row. Now, the thing that I really mean when I say all clocks are valid is, so you can ask, which one of us has the right information? Which one of us, when I go flash, which one of us has the truest representation of what happened? And the answer is every single one of us. Everybody is right. We all have different information, but they don't disagree. We are saying they disagree because we expected it to be the same, because we have this notion of a now, and there's a true story going on, and the only differences come because light has to travel through this box of space. But Einstein is telling us every single person is right. Every single person is right. And the weird thing is, if you try and say, no, Einstein, that's not how it goes, it must be that we just have a time delay that's happening, and you use that assumption to do physics, you'll get experimental predictions that don't add up. Like, if I move towards you and I shine a light, you'll measure the speed of light to be faster. We can measure the speed of light in the lab. We know it's the same, regardless of how fast the source moves. So we have to let go of trying to make all our clocks agree on some singular point, some singular coordinate for this event. We just have to let go, because at the end of the day, you can say, well, doesn't that break the laws of physics if we all have these different things? And surprisingly, no. Physics doesn't actually tell us what's happening everywhere in the universe at once. Physics tells you how things evolve at a point, at a time. You have equations and you can probe them, point and time. You say, what does the electric field look like at this point at this time? What does a photon look like at this point at this time? So it just describes how things evolve according to the clock in one point. And because we all have our own clocks, the laws of physics just have to be consistent with us. It's not that we all have to agree on an objective, singular time and event, the time and place of an event. It's that we just have to agree that what we recorded for the time and place of our event doesn't violate the laws of physics here. And it turns out that it doesn't. It doesn't, right? Because all you need, what's the laws of physics? I'll just make sure that this event here, none of us can record that this event happened faster than the speed of light could travel. As long as none of us agree that we could have received it at a signal faster than the speed of light, it doesn't matter that some of us received it, that it literally happened at a different time for everybody. That's a really weird way to think of the world, but that's really and truly what I mean when I say every clock is valid. All observers are valid. It's not just, okay, I'm elevating everybody's perspective. If anything, we're demoting. If I'm the one to snap my fingers and that's the event, it's tempting to say that I am the possessor of the true coordinates of the snap because it's my hand. But that's a human bias that we're putting onto it, right? If every place and every time is just as not special as every other place and time, neither am I. It might be my hand, but I am just a seer of events, an observer just like you. So where does that leave us? That really leaves us with a problem when it comes to now and the present. Because it's not just a thing of the math that every single one of us has different time running in our different place. It's really physically how it works. And the consequences are really physically true. So we say, okay, well, we have this illusion of now, right? I keep talking about you can Skype people on the other end of the globe. I keep talking about how it seems like the technology is the barrier to the instantaneous communication. So now we're going to do a really quick once-over of why we're going to get some really bad news on that front. Because it would be great if it wasn't, right? If we live in a Star Trek universe, so light isn't fast enough to talk across planets, we'll just invent subspace, right? So not true. It turns out that as people, we're not that great at discerning the passage of time. We can sort of tell time passing to within about 1/10 of a second. It's about as much time that can go by without us being like, oh, time is passing. So what do I mean by that? Well, here we have a picture of some guy. He's clearly taken a torch, he's waving it around, and the camera is taking a long exposure, right? So the camera, let's say, takes a 5-second exposure. So what does that mean? So the shutter is open, and light from the fire comes and it hits the camera and it stays there. And then new light comes and hits and hits. And the camera just keeps accumulating all this information for 5 seconds. And at the end of the 5 seconds, it gives you a picture, a snapshot of now to the camera. That camera couldn't tell the difference. It's 5 seconds. It's temporal resolution. It can't tell things happening on a smaller scale than 5 seconds. To the camera, that looks like a solid object or a loopy, floppy object. Of course, to us, we know that's not the truth, right? We've seen people do this before. We've seen this trick many times. We know it's a single torch and it's moving around, and if you see it in person and you don't rely on the camera, maybe there's some blurring around the fire, but you'll see the thing actually carve out the path. So this effect is not just a camera effect. This is the universe truly and very well looks different depending on how well you can resolve steps in time. And as people who can only resolve steps at like 0.1 of a second, the speed of light, which is what carries information, right, goes at 300,000 kilometers per second, right? It's incredibly fast. And if we can only discern differences of 1/10 of a second, then light can travel about 30,000 kilometers before we notice that time has passed. That is a really convenient number for a planet the size of the Earth. Okay, so the Earth is 40,000 kilometers at the circumference at the equator at its widest. Is about 12 to 13,000 kilometers in diameter. So the entire Earth fits inside a bubble of what to us is a now. And it's now not because there's some universal fundamental now, but because as people, we just really lack the resolution to tell that something is different. If we could tell that there was, if we had better resolution in time, and we could see, 1/100th of a second. We could discern 1/100th of a second. You see a hummingbird fly, and instead of, just its wings making this, you can't see the wings, right? So imagine you had such resolution with your eye that when you look at the hummingbird, you actually see its wings flap. If we had that ability, when we start to Skype people on the other end of the world, we start to run into trouble because we'll notice that beyond the technology, there's a lag there that we can't get rid of. It's just really convenient. And in some ways, we, as people who live in the 20th and 21st century, have it the worst because people in previous times didn't know this. They didn't have the feeling that technology is the only barrier to instantaneous communication. They weren't sure if it was possible, or for them it was something that was far off. Whereas for us, even as of today, it feels like we're just getting closer and closer. Internet infrastructure is getting better. We're just getting there. When really, we're just about hitting the limit of what we can do. And it might feel a little weird, because we think, well, there's like when you go to Mars and you try and send signal back from Mars, it takes several minutes, right? So if we eventually, go to Mars and people are on Mars and they have a problem and they call back and they say, help, the colony is on fire. They're not even gonna get did you say the colony is on fire for like 30 minutes? Imagine calling 911 and that's what happens, right? 30 minutes later you get I'm sorry, did you say an emergency? Not helpful. So spacefaring humans may actually think and feel very differently about time. They may not actually believe in how we feel so strongly about a present now, how it seems so obviously revealing itself to us. Might actually be totally out of the intuition of future humans because they grew up in a world where, if your parents become astronauts, you have to decide whether to stay with your friends here or to go with your parents into the future because you can't come back. You might have to decide, if you're going to colonize a different planet, if you have to go to another star system, you can't talk to Earth. Earth can't exactly be the, headquarters of it's not a Star Trek universe, basically. And I'll remind you, as weird as that might sound, for most of human civilization, people didn't think this way about time, that it was this ever-present fundamental thing of physics and nature. So it's not that big a difference to say that I think people in the future may also feel differently about time. And what we think is now is just going to be another bullet point on somebody's slide in 300 years. So there isn't really a now. We're just lulled into this false sense of it by our poor temporal resolution and the time in which we live. Okay, so I'm a little sneaky because it sounds like I'm trying to draw a conclusion on it and say, okay, well, that's why. There isn't a now, but we get away with it because of our bad resolution. But I've danced around something really fundamental, I think, which is that time seems to have a flow. And that's sort of what makes time, right? Is, okay, all these fancy things with Einstein and clocks and whatever, and I said every place has a different clock, every other clock is valid, and they all can run at different speeds, but I never said that they're not running in the same direction. Right? And time for us runs in only one direction. We remember the what's been said. We don't know what's going to be said. So in a way, maybe there's still something to be recovered about our experience, something fundamental about time, and that is the flow. Can we look for the flow of time in physics? So that's a really easy question, actually, it turns out, to answer, because some experiments you can do is you just record a bunch of physics and you play it backwards and you see if it looks different or if it looks the same. Of course, that, is difficult to do in practice, but we can look at the equations and say what would happen. And we find that actually in physics, almost everything is reversible. There's no forward or backward in time distinction for any of the laws of physics. They don't care. Electromagnetism, right? If a photon, which is mediated by the electromagnetic force, is traveling through space and I reverse time, it's just traveling through space this way. Speed of light is still constant, still the same. The energy of the photon has not changed. Nothing has changed. Charge is conserved. Any way you want to put it, it's the same. A good example is a current in a wire. This is like a standard high school problem. So you have, you send a current through the wire and moving current makes this a magnetic field. So what happens if I were to play that video in well, it's not a video, but if I was to play that in reverse, the current would just go the other way and the magnetic field would just go the other way. Okay. So what about alternating current, right? Where you go back and forth and back and forth and back and forth. Now it's going back and forth and back and forth. If I ask you, which did it start? Did I start playing the video forward in time or backward in time? You don't know. All you know is that it looks the same both ways because it's just bouncing back and forth. You don't know which one was forward or which one was backward. I would have to tell you which one I recorded. And then you'd be like, oh, that's forward. Same thing with gravity, weirdly enough. I know I said gravity and time have a connection, and I'm not going to drop that or abandon it. But gravity in the sense that things fall, or what you need to exert energy to escape the Earth, gravity also doesn't care. So if I drop a ball from a height, it starts off slowly, and as gravity acts on it, it picks up speed more and more and more, until finally it reaches its maximum speed near the ground. But if I toss a ball from a lower height, it has maximum velocity at the beginning, but gravity starts to work on it as it travels up, and eventually gravity wins when it reaches a maximum height. And it comes back down. And if we ignore, friction, and if we try and drop a ball, of course, it can go bouncing off that way, or there's a lot of friction, so it'll come to a stop anyway. So if you ignore that stuff and you just say, okay, let's look at what gravity is doing, it's just going to bounce up and down indefinitely and follow this trajectory. It doesn't matter whether you dropped it or tossed it. Again, I will show you this video and you'll be like, I can't tell which one's forward or backwards. It's easy if you actually record a video because there's a hand and trees and physical cues that we understand, but just gravity alone doesn't do it. Okay. All right, but there's got to be something, right? That said there's still some sort of flow in physics. And that something turns out to be heat. Heat, surprisingly, is the one thing in physics that is not reversible. Heat flow. Specifically, we know heat always flows from hot to cold, right? If you take an ice cube out of your fridge, you put it on the counter, you go away and you come back, that ice cube is going to be melted. Heat is going to have gone from the hotter surroundings into the cold ice cube, and the heat is going to flow until it's about equal, and the ice cube will melt, and there's your ice cube. You don't put the ice cube on the counter and then come back later to find that the ice cube is in fact colder than you left it, and your room is hotter than you left it. That's air conditioning, and you pay good money for that, okay? So heat always flows from hot to cold. It is not reversible. If you have something that starts off hot and you let it flow to cold and you leave it there and you let it sit, you will never find that it starts to separate hot and cold again. Never. And there's a law of physics for that too, that entropy, to use a technical term, always increases. Now, I made fun of Newton's law for being called a law because it was something that wasn't super fair, but the heat flow is actually solid law. Like, it applies to particles. It applies at our scales. It seems to apply everywhere. So heat really is directional. So we have to look at the flow of heat, because this could be our source of time. So remember what Aristotle said, that change doesn't require time, right? Change in its purest form, we're just comparing two different states, and we're saying, are they the same or are they not the same? Just to say whether or not change has occurred before we start adding in, is there time and is there other stuff? So I'll give you a state. Here's the two things from the diagram, hot and cold. And again, like with gravity and E&M, we'll just ignore everything else. We'll pretend like this is the only thing in the universe. So there's no air and fancy ways to get out of this, okay? So they'll just stay like that forever, okay? Now, if I put something in between them, this is what you saw in the previous image, now heat can flow, and heat will flow in one direction. And it will continue to do that until there is no more direction for heat to flow, right? Equilibrium, same temperature everywhere. And this is fundamentally an ordered process. What do I mean by an ordered process? So if you start in the top state, if I give you something in the top state, it is possible for that to change, for that later or at some point to be this state. There's a way to get from that state to that state. It is possible, right? Put something in between. It is not, if you are in this state, there is no other state for you to go into. There's no change that is possible. There is a change that is possible in that state. There is less, but still change that is possible in that state, right? It can go into this one, but it can't go into that one. So it has some room to go. And then the least room to go is here. It just can't change. Any state you pick up next to this one will be the same. So in a weird way, there is a flow, right? There's a flow toward this being, right? We don't have to assign timestamps and ask how long does it take to flow and how does all these mechanisms, we just say there is a tendency to end up like that, solely because if you start like that, you don't end up like anything else. So, so there's just like a little animation that shows. All right, so that'll just play while I talk about this. So this actually creates an ordering, right? State 1, state 2, state 3. It doesn't matter, again, if I assign them time or I say it takes an hour to go between state 1 and 2 or a million years to go between state 1 and 2. The point is state 2 comes after state 1 in some sense. All right, there is an ordering. Whatever I pick as my first state, the thing it does is it says, okay, your end state is going to be that, the equilibrium state, and I am going to get there in as few states as possible. That's it. So I'll pick a different first state. I'll pick a different initial state. I'll pick that one instead of the one where they're separate. Doesn't matter. It'll do the same thing. Okay, where are we headed? Equilibrium, like always. Okay, this is now state 1. That is still state final. And we're going to move through as few states as possible to get from A to B. And that's it. So there's an ordering that's just inherent to the flow of heat. And it's also irreversible, as we know from the law of thermodynamics and from ice cubes. And it's directional. So directional in the sense that if you start in some state, you're not just going to go to some other random state. You're going to go towards the state that most points you towards equilibrium. There's a direction. Once you take a step in that direction, you cannot go backwards. and there's an inherent fundamental ordering. Okay? So this really looks like time, because all I have to really do is just assign 1, 2, 3, 4, 5, 6, 7 to all the different states, and then like Aristotle, just say, I'm not going to notice it if it doesn't change. So every time a state changes, that's a unit of time. Okay? And that's it, period. That's it. And you can you've recovered the aspects of the flow of time, the direction of it, the irreversibility of it, the ordering of it. And so why does it feature so strongly in our life? Because we're thermodynamic beings. We feel like, no, hold on. It must be that time is ticking by that allows the thermodynamics to happen. That's sort of like what we want to say. But that's, again, it's from our approximation as thermodynamic beings, what we call living. We can't imagine, try imagine living in that 5 seconds where everything was frozen. You can't. You can't live without your biological processes turning at least a bit, right? You can't imagine living for even a fraction of a second unless some experience has occurred. We don't even define our own life process outside of thermodynamics. And what we've done is we've taken the flow of heat and we've mistaken it for something that we call time, and we've expanded that to say, well, time is everywhere and it affects everything, when it doesn't. We're just not reversible. Us. Photons are reversible, gravity is reversible, most of the universe is reversible. But us and everything we interact with is not reversible. So that leaves us in a really weird place. Okay, so I promised some sort of resolution to the answer, what is time, or something to feed you. And I sort of danced around everything and destroyed everything we like. So I'll sort of wrap up with that our experience of human time is real. Okay, this talk was not meant to like break how you experience your life. Like I said, I think humans have probably been having this lived experience for tens of thousands of years. So I'm not trying to diminish the human time. But what I am saying is like, time maybe is not the right word for it. It's the human flow of thermodynamics. And it just so happens we called it time first before we discovered the physics time, and they share the same word, and maybe that's unfortunate. But it's not a fundamental feature of the universe. The thing we experience is time. If you look to physics and you say, where is this? The best physics will offer you is say, it's thermodynamics. You have non-reversible processes going on, and that's it. Physics, the time in physics is just a probe of gravity. It isn't really related to what we call time. That's why maybe in 500 years we'll have different words for both these things, human time and physics time. Because what we experience doesn't tell us anything about gravity. Time just happens to be useful in science to tell us about gravity, but that's it. But there's no conflict between these two, because we're not breaking the laws of physics to reconstruct human time out of physical time. We're saying, look, it's a two-part process. We've got the flow that's given to us by thermodynamics. We share that in common with the universe. But we also just happen to be living at this time that we're creating the illusion of now. We feel like we're exploring a shared present. And that's less a product of the fundamental feature of time, of the universe, and calling time a fundamental feature, and more just almost a cultural product of where we are technologically and as a species, and literally biologically in relation to the size of our planet. So physics time and human time are two different times, and you can very much ask what is each one of them, but you have to ask them separately. And in one, the answer is disconcerting, that it's thermodynamics, and in the other, it's equally disconcerting, that it's nothing fundamental, and it's just probing gravity. So that's it. I hope I've given you guys something to think about. Thank you.
I should say something quickly, like we've got some time for you, but anyway, wow. All right, we'll have coffee tomorrow and talk more. At any rate, questions for Richard, please.
What do you think about Lee Smolin's book, Time Rebound? He thinks the time is fundamental.
Yes, that's right. So Lee Smolin, great writer, he's a great physicist. So this is actually, so Lee Smolin has a point, right? So he says, no, there is something fundamental about time. I have to actually admit, this is not a super consensus thing. It's the view of most physicists that time is not something fundamental. That's the direction that people are starting to think now, especially since Einstein. But not everybody's convinced. And Lee Smolin is one of these people who's not convinced. He doesn't believe that you can... he doesn't believe that time is not fundamental because in his view, you can't remove a person from the world they're measuring. So for Lee Smolin's perspective, even quantum mechanics as we understand it and everything as we understand it, we understand it through our interactions with it. And our interactions experimentally, they unfold in time. Things happen in time. And time is something that's fundamental to the universe that we interact with. And so his perspective is, if it's so fundamental to everything we measure and it's so useful in parameterizing how things seem to change, how can it be something that's just approximate? How can it be something that's only, good for humans and maybe not if we could experience other things? And he's not the only one. Other people ask that question. I think it's a valid question. But I think the evidence is just stacking up so hard in the other direction that it's hard to make that case. That's why he writes a book about it.
Hi. I'm over here.
Sorry. I saw 2 microphones. I was like, what?
Yeah. So in terms of this, it's definitely something to think about. So the teleportation experiments, because everything is there, and in all the places all at the same time, how does that
factor in? So to speak? Yes. That's a good question, right? So that's something that's also new, is teleportation and teleporting quantum information. So obviously, when you think teleportation, you think Star Trek and you move people and stuff. But in the lab, the version of it that we've got working is you've got a particle and you want to transport the particle from point A to point B. And we figure that, okay, we can't actually take the particle and move it from point A to point B. That's not really how it works. That's not how transportation is going to go. But they found ways to take information about that particle and transfer the information and impart it onto the other particle. So it's not... it's really easy to do with particles because in order to describe a particle fully, I need like this many pieces of information. But in order to describe, say, like a person fully, I have no idea. Crazy amounts of information is needed because we're so many particles and everything. So when I said time isn't a part of the world of objects, isn't a part of the world of particles, but is a part of the world of objects, that sort of comes into play here. So to a particle, time is the same forward and backwards. So if you send information from here to a particle over there, the particle isn't really going to care whether the information is outdated or whether it should be moving this way or has this happened yet or whatever. All the information that you can move from particle to particle is not time dependent. And so in that sense, moving across space and moving across time doesn't change the information. There's no impact on it. You can freely move it around in space and time because it doesn't listen to space and time. Sort of like dark matter doesn't listen to light. Right? The whole thing about dark matter is we feel like there's got to be extra mass out there, but we don't see it. So whatever it is probably doesn't interact with electromagnetism because that's the thing that produces light. So in the same way, the information that we can transport doesn't interact with gravity, with time that way.
Your topic sparked an interesting discussion on the chat stream. Here's a question from Mark Wiesel. He says, I've read Sean Carroll and love this topic, but it has never clear to me why time slows at a faster speed, because speed is relative. You say, I'm going the speed of light, but I say, no, I'm still. You're going the speed of light. So whose time is slowed?
That's a really good question. So that's one of the, so the thing about relativity is it seems like all the good information or all the interesting information comes from really tiny, subtle points. And unfortunately, as great and solid as a question as this is, the difference is in a really tiny, subtle point. So it's true, if there is no absolute time, how can I say that time is slowing or quickening, right? It doesn't make sense. Or how can I say that one is quickening compared to another when there is no absolute measure? So the key thing about relativity is if you want to compare clocks and you want to say, well, one has become desynchronized with the other, is you have to, the clocks have to be in the same place twice. Once when you synchronize them, because they have to be synchronized to the master clock of this point in space, right? They have to be synchronized to the same master clock. There's no master clocks in the universe. There's one for every point. So my two clocks better have started and synchronized right next to me, okay? Now one clock goes away onto the plane or whatever, and it's tempting to say, well, light will travel from that clock to me so I can read the clock as it's moving and I can see all these different effects. But really, that's not quite true, because what's happening is the light travels to you and it reaches you, and as we talked, right, that's an event. Light reaching you is an event, and events have no objective time or place. So whatever the clock says, if you're just reading it remotely, you can't trust that reading, because that reading is delayed, it has no specific time and place, and that clock in a different place is now marching to the tune of another master clock. So in order to have any sense of comparing times, that clock that went on the trip has to come back here. It has to come back here, and we have to look again. This clock stayed here the entire time, and it chugged along to this master clock for this point the entire time. That other clock went away and came back, and in that intervening period, it chugged to other clocks. And when it comes back, it's now chugging along to the same clock. And now we can take a difference, and we can ask, is there a difference? Are they out of sync? Are they out of sync with respect to the clock here at this point in space? So it sounds like it, it almost sounds like that's sneaking out of an answer. It sounds like such a subtle point that it should matter that way, because the way we interact with the world is visually, and it doesn't bother us that we're not in the same place always. It would be bothersome if we were always in the same place as everything. But that's how it goes. I mean, the question actually raises the point in this, the twin paradox. So you have twins, they're 30 years old. One goes on a spaceship, goes near the speed of light, and it comes back, or goes near a black hole and comes back, and they're younger compared to the twin on Earth who is aged. If they don't actually come back, you can't say that one is younger than the other, because it's true, all speed is relative. So one twin is moving away, and you're on Earth, and you're like, well, he's moving really fast, so he's got to be aging slower than me. And the twin is moving away, but they think they're standing still, and it's the Earth that's moving. So like, oh, well, no, the Earth is moving really fast. I'm the one who's going to be older. My twin is going to be younger. And you say, well, how is this possible? How can you both be the older, the young one? And the key is one of you has to return. One of you has to turn around and come back so we can compare our clocks here. And when that happens, when that turning around happens and you come back, one clock has taken a different path than the other. And we like to think of this is getting to a long answer, but I'll leave it at one more thing, which is we think of distance. Like, it's easy to think about distance. The path I take, right? I walk up and down. The distance I travel depends on the path I take, right? I can go way out of my way to walk a path, or I could walk the straight path. We don't think about it, but in the same way, time is a path-dependent quantity. If I go towards a black hole and I come back, I have gone through less time, just as you go through less distance in other senses, than if I didn't. And that's what's happening when you're comparing clocks, is one of you is going through less time, just like you can go through less distance, and you're coming back and you're seeing that deficiency, but only according to the master clock here.
Okay, sorry. So would this be the open debate that started with Niels Bohr and Einstein with quantum mechanics?
Well, yeah, so this is actually related to that. So one of the things quantum mechanics tells us is there's this thing called quantum entanglement, which, if two particles are in this state entangled, then if you learn information about one of the particles, you can surmise the details of the other. And Einstein had a problem with this, because he said, well, if I have two entangled particles and I move one very, very far away, and I measure one of them here, I can surmise information about the other. And that particle is very far away. That information shouldn't be able to travel from that particle to me faster than the speed of light. There shouldn't be anything like instantaneous information. And so Einstein said, well, there's got to be something wrong with quantum mechanics. It's making this prediction, and that's ridiculous. That's not, I think there are cases to be made, and that actually have been made, that there isn't this isn't actually instantaneous, and there are all sorts of sneaky ways of trying to get around it and saying, well, no, they're both valid. And I mean, Einstein certainly was there at the birth of quantum mechanics. It's weird to say, but we know a lot more about quantum mechanics and relativity than Einstein ever did, because the development has continued in the 60, 70 years since he's died. And so fundamentally, there was a time reason. He didn't like this instantaneous thing. That's why he didn't like quantum mechanics. But unfortunately for Einstein, quantum mechanics has also proven to be right almost all of the time.
So my question is that since we are thermodynamic beings, and so are other animals and creatures, are they experiencing time different than us?
Yes, it could be actually. So that's a good question, because I heard recently that they've actually been doing this study on like insects and things that have a high metabolic rate. Right? So if you have a high metabolism, like rats, things that move really, really quickly, they are also thermodynamic beings, and they have thermodynamic processes, and they go through way more than we do in the same amount of time, quote unquote. And the question is, okay, well, are the rats moving really quick? You know, do they have really great reflexes, or do they sort of move? Do they see us in slow motion, right? Do they have better temporal resolution than we do? And there's actually, I mean, it's hard to do because they're animals and you can't just ask them, but there's some evidence that actually like insects and things that have a really different metabolism than us on a smaller scale do have a different perception of time. You know, that when you go to swat a fly, it's not that the fly has the world's most amazing reflexes like nobody's ever seen. It's that you're moving pretty slow to the fly. Like for you, there are 5 states between I'm raising my thing and I'm hitting the fly with it. And for the fly, there's like 5,000 states. So by the time you're on state 5, he's like, I've gone here and here and here and here, and now I'm out the window. Well, they're not out the window, but you know. So yeah, and that it really raises interesting questions about what qualifies as life, right? Because plants are also thermodynamic beings. They're not net zero. And what does that mean for, you know, it's weird to think that the perception of time could be in a non-fish or mammal or something, but, you know, there are these weird implications. And if that really is the case, then these have to be explored, and it could be, yeah.
I have a question about...
Hold on, to do... There's a guy behind you.
Oh, I see. So, it's on. With the local time being different everywhere and correct in every place, and you know this question about has Betelgeuse gone supernova or not? So I think you're saying we can't say, but could it also an answer be that in a way? That kind of question is meaningless.
Yes. Yeah, that kind of question is meaningless because it's tempting to say that if we receive the light from Betelgeuse going supernova and it's some distance away from us, it's tempting to say, oh, it must have gone supernova earlier. But again, that is doing that thing where we're ascribing objective time and place to the supernova of Betelgeuse, when in fact that happens whenever you see it happen. It doesn't matter whether somebody else saw it before you, as long as they followed the laws of physics where they are and you're following the laws of physics where you are. So it's true. In in Newton's picture, it was nice. There's a here everywhere, and we're only light time travel delayed from each other. But in Einstein's picture, it's meaningless to say here and now are similar words. You can't say here in Beijing, right? Here, we're in Toronto. I have to go to Beijing and say here in Beijing. And in this way, Einstein's saying it's the same thing with now. Now, anywhere but here is a meaningless term. It's meaningless. There's no now in Beijing for us. We'd have to go to Beijing. It's here and now. It's not there and now. So, yeah, it's totally, in a way, it's totally a meaningless question.
I'm trying to think so hard of this in terms of a question. I mean, the whole meaningless thing, it makes it difficult to phrase this as a question. But on the RASC Facebook group this week, we were having a discussion about the passage of time on Mercury. Like, could we build a Mercury calendar? The problem being that the length of a year in Mercury is 1.5 Mercury days. The length of a Mercury day is 2/3 of a Mercury year. And how could we build a calendar based on that? we thought maybe the best thing would be not to measure days as the base unit of the calendar, but to measure years, because the rate of the sun around Mercury changes because of its eccentricity. Getting away from that a little bit, though. But units of time that we have to measure are, they eventually sort of break down. Any kind of clock that we build is basically, as you've said, it's a mechanical simulation of thermodynamic processes. But one thing that you didn't mention when you got into discussing thermodynamic processes is sort of the main thermodynamic unit of the universe, which is stellar, what we call evolution, or as you were saying a few minutes ago, metabolic processes. Basically, the mechanical processes of winding down inside a star are those thermodynamics.
That's a good question. I think so. I think so, because you know how I said at one point, if you play, a good way to tell if something is time reversible is to play a video back, right? And I gave these examples of the wire and the ball, and you couldn't tell forward or backwards. But if I play a star in reverse, that looks really weird, right? Now, instead of a source of energy, it's this huge sink of energy, and heat is flowing into it, and it's almost like a black hole in this weird way. It's a destination for all light in the universe. And so it's definitely got to be thermodynamic, because it's not time reversible. And it's the laws of thermodynamics that actually tell us how the star evolves through its core and all these other stuff. So, but it is interesting to note that, with thermodynamic time, these are the processes that you see. If you have relativity of time dilation, like let's say you look at a star that's moving away from you very fast, that's far away. And you say, well, I know if it's moving far away from me, it should appear to move slower. I should receive less and less updates from it. And so what that means is you're going to see the thermodynamical processes of that star evolve slower over time, right? If an atom was going to go hit here and go here, you're receiving updates very slowly. It's going to be like update, update, update. It'll still do the same thing, but it takes longer, right? So in a way, so what was the point of that? Yeah, I mean, I think it's all to sort of point back to the fact that these are thermodynamical processes, because if you observe a star going in slow motion, all the processes that make a star towards the end of its life go supernova will happen slower. If you could predict how long it should take to watch that star blow up, and it's really moving far or fast away from you, you'll see that happen later. It really will take longer.
Weird thing about the Mercury discussion was we figure it's probably easier to have a frame of reference on Mercury that's based on the length of the day, or rather the length of the sidereal day rather than the synodic period, because the period of rotation of Mercury doesn't change. And if you did happen to live on Mercury, it would probably be easier for you to go out on the surface and explore at night, because you didn't have the sun there boiling everything to bits. And that gets back to thermodynamics, because it's easier to explore the surface of Mercury with some kind of heat pack that keeps you warm than going out on the surface during the day and having a massive air conditioning system to keep you cool, which would create more heat.
Yeah, well, and that's exactly it, right? That's the heat flows from hot to cold, which is, it is actually, physically speaking, it is so much easier to have something that radiates heat into your cold space than to expect that your cold space is just going to stay cold or get colder. So that is exactly why.
My understanding is, doing supernova studies for very distant things, the universe seems to be accelerating. And I've seen studies that say it started either, and I don't know the right number, but 11 billion years after the Big Bang, or whatever number billion before us. But if there's no such thing as an absolute time, how does the universe that's in that direction know that it's time to speed up when the same much as the universe in the other direction? And anyway, I'd appreciate your thoughts.
Yeah, that's a great question. 'Cause that's one of the things that this always opens up is if time is not as we think, how does the things that we think of time in terms of time behave? And there's a couple ways to go about that. So one of them is, the history of the universe as it's talked about, you know, the 13.5 billion years since the Big Bang and all the, you know, first stars and then the galaxies, in a way, although most of that is driven by gravity, that's still a thermodynamic thing that we're investigating, right? We're investigating stars and the light from stars. We're not able to, actually just now, right, we're able to measure gravitational waves, which are not thermodynamic in nature. It's sort of like the first time that we can make a measurement of something that that isn't strictly thermodynamic. So when we create the history of the universe and the picture of these things happening and evolving, they're evolving in this thermodynamic time really nicely, the same way that we are. And so we can set timestamps to them, and we can say this happened at this time and this will happen at this time. But it's not that, yeah, it's more of a relic of the fact that we interact with the results of thermodynamics, and that's how we parameterize it. Like, in a really weird way, if you ask a cosmologist, you know, how old is the universe, most of them have been trained well to say 13.5 billion years. But if you find one, you know, who speaks off the cuff, then they can give you weird answers like, we actually don't know, or it might be infinitely old, or it might, and they're taking into account all these other things, all the other possibilities of the universe beyond the charting of history that we normally do in astronomy. And so for the record, for you know, for normalcy and convention, they adopt this thermodynamic history. So that's why, even if dark energy isn't exact, that's what we think is causing this accelerated expansion. Even if that's not thermodynamic in nature, you know, it's pushing apart the stars that produce the light that we receive, and that's how, or in this case, the supernovae, which is how we, you know, measure that the universe is expanding. These things are glowing hot objects. It pushes them apart, so they do their thermodynamical processes from farther away than we would expect. So we still get to parameterize in terms of time, even though this effect could be driven by some dark energy that we don't really know what that is.
Yeah, I think I was actually going to ask a somewhat similar question in more or less sort of what does that whole picture do to, you know, cosmology in general, basically. But is it correct then to say that you could, I guess, put together a coherent history, if you want to put it in those terms, a cosmological history of the universe, just based on, say entropy as a parameter instead of time per se, related to, you know, our sort of local time, and you'd still have something that's pretty similar to, like you said, sort of the standard kind of everyday answer you might get from a cosmologist. Is that
Yeah. So like I kept saying heat flow, but it's entropy that's increasing. And from a cosmological standpoint, you know, we can look further and further back and see earlier and earlier galaxies, but then we sort of hit this wall with the cosmic microwave background, which, when the universe was very young and there were no stars or anything yet, it was just gas, and the gas was glowing hot and it was radiating. And so this light has been sort of traveling from this cloud of radiating gas ever since. And that gas that produced it is opaque, so there's not light that shined from earlier that can come through it. We can't see light from before a certain point in the history of the history of the universe. And that point, the point the cosmic microwave background is about 300,000 years, 400,000 years after the Big Bang. And by that time, we're well within the realm of increasing entropy and thermodynamics. You know, we basically, even what created the cosmic microwave background is a gas. It's a glowing gas, and then it becomes stars and those processes that. So by the time, basically as far back as observational data currently allows us, we're already still working in a thermodynamic context. Where things get really interesting and where the cosmologists have their fun is when you try and predict what's happened before that we have yet to see, and you have to get down to really small scales or right at the beginning, and then they can do, you know, weird things with, you know, quantum gravity, like the new thing everybody's trying to find. But certainly when it comes to observational evidence, even cosmologically, we're well within a thermodynamic time frame.
So I know you said, well, if tomorrow we see Betelgeuse going supernova, as you said, we shouldn't be saying immediately, well, that happened in the year 1400, whatever. So, and following on from the last couple of questions, I guess, we keep hearing that we're going to build a really big telescope that will look far back in time. But that sounds like that's not quite the right way to think about what we're seeing.
That's right. So I'm sort of guilty of jumping back and forth a lot between, when I say we look back out and we see farther back in time or we see earlier galaxies. And true to the spirit of this talk, that's not actually quite true. It's not that these are things that are older and we're just seeing the earlier light. For all intents and purposes, that is, if you look at, you say we're receiving light from a galaxy and we, compare it to galaxies that are nearby, and we find that its structure is that of an early galaxy, one that's just formed. Maybe it's 1 billion years old. If you want to ascribe an age to the galaxy, probably the most correct thing to say is that galaxy is 1 billion years old here and now. Because although it's tempting to say, well, no, it's 13 billion years old like the rest of us, and maybe there's aliens on that, and blah, blah, blah. If that were true, any consequences of that being true, it doesn't matter, because that information can't travel faster than the speed of light. Information about that thing being any older than it looks will never overtake the information about the thing aging. So, as we were saying, it's sort of a meaningless thing to ask about now in other places. So the best thing you can do is to say that whatever time you record is the time. So Betelgeuse didn't go supernova in 1400, for example. It went supernova now to us. And it's really weird to say, well, what do you mean now to us? You mean now at a certain time and then now to different people later? No, now to us is 100% as valid as being right next to it when it blew up and saying it's the year whatever. So, yeah.
If we've got one more question, and then we'll move on to the next part of the evening. Any more questions?
If at some point in the future expansion of the universe would change to contraction of the universe, would it mean that the thermodynamic flow can in fact be reversed?
Not that it would be reversed. Probably it would. How do I say? It would still be something that looks different forward and backward. Because if it starts to contract, then we know, for example, how contracting gases behave. We would expect them to heat up, and we would expect certain behaviors from actually, you're right. So yeah, gas is not a good example because it would heat up if you reversed it anyway. Stars are a good example. They've been made, and if the universe starts to contract, you won't see stars become unmade. They can collide and then they can disperse, or they can get sucked in a black hole and torn up and stuff, but it is not the same as the reverse process. The star won't suddenly go from fusion to fission and then disperse into a cloud and then go from a disk to a big cloud, and then it won't happen that way. And so it's more of a thermodynamic. Even if the universe were to recontract and come back to a point, that would still be considered the future from now. It wouldn't be like a time reversal.
I think it goes without saying that you've given us a lot of food for thought, and that there'll be a lot of interesting Facebook chats and sleepless nights. And I'm glad I now know why I'm an observational astronomer, because this just blows my mind. Thank you very much indeed, Richard. We have a token of appreciation here, and then Ralph will take us out for the rest of the evening. So thank you very much.
Don't go away. Don't go away. I was going to say that, time is one of those things that we never seem to have enough of. And we seem to spend a lot of time, thinking about how we're going to record it, how we're going to watch for it. We spend a lot on trying to record it and keep track of it. I was thinking about what you were saying about time, and it occurred to me that, we've all got cell phones that have these infernal clocks in them, and a lot of us keep on looking at them all the time. My 2-year-old grandson is now starting to look at clocks. So heaven knows what he thinks about this concept of time. But, you know, it is something that really captures our imagination. And you got a lot of really, really good questions tonight.
Yeah.
Really challenging ones,
Yeah,
right?
really good ones, yeah.
So, you know, I think it goes without saying that, you know, we are consumed with the thought of time. So I think it's really appropriate that, as a little token of appreciation, I'm going to give you this calendar so that you can record all of your events.
Thank you very much.
Thank you very much.